In this course, we talk about the statistical inference, because the statistical inference play an important role in the theoretical statistics. Statistical inference has moved behind the real data which are obtained from the empirical study, either experimental or observational. Statisticians have tried to use statistical inference as a tool to analyze the data, to help scientists to find some conclusion to their questions. Suppose a certain set of the data are collected by scientists, which call it sample value or samples. So our starting point in the statistical inference is the data which collected by the experimental or observational study, and we denote it by the x. In simplex cases, x is a vector of the number, as denoted by the x, x1 to xn, but maybe have some complex structure. To find the answer to the questions of the scientists, we consider the value x as a random variables. The random variables have an unknown distribution fx. The all possible value of the x is called sample space. And we want to talk about the fx and choose the convenience fx for the data. We denote the set of the all value of fx by the f and call it statistical models. There, the statistical models is the set of the fx, which known mathematical form, but depends on the unknown parameter theta. When the theta belongs to theta, which is subset of RK. For fixed theta, fx is a distribution function. Its support is Rn. In majority of the cases, all distribution functions are member of the f refer to either discrete or continuous random variables. But it is possible if belong to mixture of the discrete and continuous variable. The theta is called the parameter, and the possible value of the theta, which is denoted by the big theta, is called a parameter space. So we call fx as a parametric statistical models. If you want to have a picture of the structure of a statistical inference, we can say the figure 1.1. In fact, the statistical models start from the data uh, has a form of random variables in the statistics, and in random variables has distribution which depends of the parameters. So we want inference about the unknown parameters in two ways: estimation or testings. And the estimations are point estimation or interval estimation. We use statistics from a random variables to make this statistical inference. For example, let x1 and x2 sample independent sample from the normal theta and 1, which density f(xi) theta. If we consider x as x1 and x2, the set of x has two-dimensional normal with mean theta, vector of theta, and identity matrix I do, and distribution of x equal fx1 and fx2 because they are sample independent. Example 2. Consider a one-dimensional density function f g x as a called two-parameter exponential distribution. The parameter in here is a theta 1 and theta 2, where theta 2 is positive and x is greater than theta 1. So the parameter space is the theta, which include theta 1 and theta 2, which theta 1 belong to R real value and theta 2 belong to positive R, and the sample space for every theta is include x belong to R and x greater than theta 1. The union of x theta is R. In the statistics, we define some function of the observation data, or here is a random variables x. A function of x is called a statistics. So the statistics is a real value function of random variable belong to samples x, which has density function g t theta, and we use tx to make inference about the theta. Definition 2.1: a function t from the x to r for some positive integer r such that tx does not depend on theta is called statistics. The value t equal tx corresponding to observed value of x is called sample value of statistics t. The conditional tx does not depend on theta is needed to make sure that the statistic is computable. Some example of the statistics for a sample X are as follows. For example, T1 is the summation of xi, T2 is summation exponential of xi, T3 is the set of summation of xi and summation of xi2, and T4 include x1 to xn when x1 to xn are order statistics. Order statistics means the first observation is less than second and so on until xn. So the statistics may be one-dimensional, two-dimensional, or even n-dimensional. Sometimes we shall consider the inverse image of the t, of the statistic t, as a set of EAT x include x belong to x and tx is t. For example, if t is the summation of xi, a single set EAT include x1 to xn such that x1 plus x2 to plus xn is t. Why we use statistics in a state of x1s to xn? Because tx summarize the data. If look at x is n-dimensional, but for example t1 is one-dimensional. If I have a one-dimensional statistics which include the information of the samples, it is very easy to use of t replace of the sample x. So statistics are very important in the statistical inference because the base of the statistical inference is the statistics. In the next section we talk about the statistics, type of statistics, for example sufficient statistics, complete statistics, ancillary statistics, the relation between statistics and the family of distribution. We can find easy statistics, every kind of the statistic in this family, which called exponential family. All of this subject is a study in next section. So is this in this section we have some information about the sample space, parameter space, statistics, sample and distribution, and statistic and the main point of this course is on estimation, and the next course is about testings. So first we tried to find some information about a point estimation, and point estimation is based on statistics. So first we talk about the statistics, and in the second point we talk about the point estimation, and last one we talk about a optimal point estimation. So this part or subject we study in this course. Statistics include different type of statistics, estimations, method of estimations, point estimations, and optimal point estimations.